Great. Thank you for the invitation to speak. Couple quick things. These slides are available if you'd like to follow along. If you go to my website, I have all of my slides. You can search for the one that's OSU. Actually, I'll just post this in the chat as well. Also, I'll post a few links for resources once we let people trickle in. The stuff I'll talk about today near the end, which is my joint work with Eric Katz and Joe Rabinoff. We wrote a survey paper actually about this work, which I recommend reading. And then there are several other good survey papers about the area that we also recommend. So let me put the slides in chat if you'd like to follow along. Here we go. So I'll actually postpone talking about tropical geometry basically until the end of the talk. And I'll speak most about Diophantine geometry, so solving equations over the integers or rational numbers, and arithmetic geometry. This picture, though, in the survey paper that I just referenced, Joe Rabinoff made a bunch of beautiful fractal-looking pictures that explain what's going on. And I'll try to explain a bit about what this picture means and how it helps you do number theory in this talk. But to start, here's the basic, this is a colloquium, so here's the basic problem, the really basic one. You have some polynomials and some number of variables, let's just say with integer coefficients, and you want to solve them. You don't just want to solve them over the integers, but over lots of different rings. Maybe integer versus rational is interesting. The real numbers is easier, but is interesting. Complex, even solving them with other polynomials or solving them mod p. So the general setup is some polynomials and a ring, and you want to find this, set of n tuples of elements of that ring, which solve the equation. And it's a fact that solving equations is hard. In fact, it's provably hard. So Hilbert's 10th problem, it's just about the ring R equals Z. And Hilbert stated this problem as devise a procedure by which, well, it turns out what he thought we could do, we couldn't. So it's a theorem from the 60s and 70s that there does not exist an algorithm, so a program in Magma or C or Python, which solves the following problem. Input some polynomials and output, forget about all the solutions, just yes or no. Is there an integer solution to your equation or set of equations? So Hilbert, maybe it didn't occur to Hilbert that it wasn't possible to find an algorithm. He did say devise a procedure by which. What this really means is, there's no way to do this. The obvious things you can think of, like, we'll try 0, 0, 0, 0, 0, 0, 0, 1, brute force. That's not an algorithm. If there is a solution, that will find it for you. But if there's no solution, your program will just run forever. And so the hard part of this is, or the harder part of this is detecting whether there is no solution and knowing that with certainty. If you know about logic, this reduces, like most things, to the halting problem in theoretical computer science. On the other hand, there are algorithms for other rings. Over the complex numbers, it's a geometry problem. It's just a question about dimensions. Over R, it's geometry plus you can use a little bit of logic, elimination of quantifiers. Over a finite field, you just try, if you're working mod true too, you just try all zeros and ones. So there's, in QP, CT, there is sometimes when there's a nice algorithm, but it's actually even unknown for Q. If you forget everything else from this talk, go read about this. It's crazy. We know the answer for Z, but we don't know the answer for rational numbers. It's still open. I think the answer is no. So here's an especially difficult equation to solve, or family of equations. Taylor, Wiles, and others showed that the only solutions to the equation x to the n plus y to the n equals z to the n for n at least 3 are the obvious ones, the solutions where one of x, y, or z is 0. So this is a problem that has inspired many number theorists to go into number theory. The story is that Andrew Wiles had an idea for how to solve this and kind of kept it to himself for about 6 years. So he was already a professor at Princeton, he had some other stuff that he kind of wrote up in the meantime, but was, was mostly working on this. After 6 years, he solved it. And this took 300 years from Fermat's, note in the margin to prove. Famously, there was a gap in the proof, but after another year, they were able to fix it. Now, this isn't just a bad joke. The Gap Jeans company actually approached Andrew Wiles about doing a commercial. Andrew did not find this tasteless, but he also didn't want to do the commercial. He was also approached by Barbara Walters to do a 60 Minutes interview, which he declined. He does now work at Oxford and has a building named after him, but doesn't like the limelight. So in Diophantine and arithmetic geometry, I kind of like to phrase the different type of questions you consider like this. So qualitative, does there even exist one solution? That's already something that you can't do with a computer, unsolvable. But for certain special equations like Fermat, sometimes you can find them. Do there exist infinitely many solutions or finitely many? Does the set of solutions have some extra structure, geometric structure, group structure? There are quantitative questions like, how many solutions are there? 0, 1, 10. How large is the smallest solution? How can we explicitly find all of the solutions or find them with proof? These are actually two different questions. Sometimes it's still difficult to conjecturally find all of the solutions. And I'll show you examples of all of these. But the implicit questions are, why do some equations have solutions or fail to have solutions? Why do some have many and some have none? So what kind of underlying structures control this? So I keep saying Diophantine geometry, arithmetic geometry. Part of what I find interesting about my field is that geometry, things like the curvature of a surface, when you think of it over C, have some relation to the solutions to that equation over Q or even over a finite field. So an example of what I mean by geometric structure is Pythagorean triples. So lemma, this equation has infinitely many non-zero coprime solutions. The geometry jumps right out at you. It's homogeneous. If you divide by z, you get a circle, x squared plus y squared equals 1. And you can use the circle to parameterize the solutions. One solution is -1, 0. And then if you have a solution x, y, if you draw the line between them, you get a parameter t. In fact, t is just the slope of this line, the way I've set it up. And if x and y are rational, t is rational. Conversely, if I have t, I can draw the line between this fulcrum point and 0t, and I get a point x, y. And these are just lines and circles, so you can write out the formula. So there's a bijection, it's reversible, it's algebraic, it's given by polynomials. And you can rephrase this as the solutions are, with the exception of the point at infinity, are all multiples of these triples. You can parameterize them. This is an example of what we mean by geometric structure. The Mordell conjecture. So for example, this equation has infinitely many solutions. If we increment the exponent of x, we get higher degree equations. When that exponent n is at least 5, it's a theorem of Faltings. Well, actually, you don't need Faltings for this. You can do this one by hand, but that this equation has only finitely many solutions. So for fixed n, this fixed equation has finitely many, whereas this had infinitely. More generally, a special case of Mordell and Faltings is that the equation y squared equals f of x, as long as f is square free, meaning when you factor it into irreducible polynomials, there are no repeated factors. And if it has degree at least 4, then this fixed equation has finitely many solutions. Now, you need some hypotheses, because if I put y squared equals x to the 10, you can just write down by hand infinitely many solutions. So this was conjectured in the 1920s. Faltings proved this in the 80s, and he got a Fields Medal for it. So there's some content. This conjecture, or rather Faltings' theorem, gives you some insight into why some equations have solutions and some don't. So Fermat's last theorem, okay, if you're not careful, this looks like a surface. You have one equation, 3 variables, but it's homogeneous. You can divide by z. and you get one equation, two variables. This is a curve. And what the Mordell conjecture generally says is the following. So in this example, on the left, this is a plot of the real solutions to this equation. I made this using Sage. On the right, I clearly did this by hand. My graphic design career did not last long. And so the left is the real solutions. The right is the complex solutions. And the complex solutions to these equations, these give you a manifold that is homeomorphic to a two-hole torus. And the way you should think about this is the cross-section of the slice of this torus. So the genus of a curve is the number of holes in this torus. The conjecture of Mordell, more generally, is that a curve of genus at least 2 has only finitely many rational solutions. So I think of this as one of the cornerstones or the big examples of what people mean when they talk about a relationship between number theory and geometry, right? The number of integer or rational solutions to some fixed equation depends on the algebraic topology, the picture you get over C. And if you prefer curvature, genus at least 2 is the same as saying this manifold has negative curvature. So back to Fermat, what kind of insight can this give us? Well, these are curves. What genus? How many holes do you get over the complex numbers? There's actually a nice formula as long as things are smooth. This is a curve of genus n-1 choose 2. So when n is at least 3, that fixed Fermat equation by the Mordell conjecture, now Faltings theorem, that fixed equation has finitely many rational solutions. And then Fermat's last theorem's the Hail Mary. It's all in at once. This also tells you something interesting. When n is 3, that expression is 2 choose 1. Sorry, 2 choose 2, which is 1. And so this has genus 1. This is actually an elliptic curve. And we were just lucky. If we add coefficients, these are called twists of Fermat equations, you can choose A, B, and C where the cubic equation has infinitely many solutions, but the degree 4 or higher still have finitely many. So here's another elliptic curve. This is an ancient problem. The problem is the following. Given an integer, 6 in this example, does there exist a right triangle whose side lengths are integers and whose area is 6? So for 6, you can just write it down. Here it is, 3, 4, 5. It's the first right triangle you think of, and its area is 6. So we say that 6 is a congruent number, not congruent as in reducing mod p. It's just an old word. And if you phrase this algebraically, well, you get two equations. You get sum of squared, so you get it's a right triangle, so you get this first equation. And then you get an equation for the area, xy equals 2 times 6. This is not homogeneous, or the second one. This actually gives you a curve. So it's 2 equations, 3 variables. And there's a way to compute the genus of these. In this case, a junction. The junction formula is the easiest way. But this turns out to be a genus 1 curve. And it's a famous old problem to understand which numbers are congruent. The most interesting small one, in my opinion, is 157. I mean, for a couple of small values like 1, I think Gauss, or maybe it's Euler or even older, maybe Diophantine, was able to work out that 1 is not congruent. So 157, it turns out, is a congruent number. There is a right triangle. Well, if you interpret appropriately, there's a right triangle with rational side lengths, x, y, and z, whose area is 157. So what's interesting about 157 is that if you assume $1 million worth of conjectures, meaning the Birch and Swinnerton-Dyer conjecture, that conjecture predicts for you, or if that conjecture is true, it tells you that there is some solution to this pair of equations and rational numbers. But the conjecture doesn't tell you what the solution is. It only tells you that there is some solution. So this pair of equations, in fact, has infinitely many rational solutions. But the $1 million conjecture doesn't tell you what they are. You can ask, how large is the smallest solution? And how many digits does the smallest solution have? I was trying to set up a poll using Zoom, but I'm gonna skip that. I won't make you unmute and guess. Well, here it is. So to fit z on this slide, I had to factor the denominator. The denominator has 44 digits. So this really is a needle in a haystack situation. Makes you wonder, how did anyone ever find this solution? Well, okay, if you know what a Heegner point is, it's via Heegner points. But the next solution, or the next smallest, has 176 digits. It's crazy. So here's a back of the envelope calculation I did in 2011. I have not updated this. On Emery's computers, you can, if you were to just check 0, 0, 0, 0, 0, 1, etc. So brute force, Emery's computers in our cluster could do numerator and denominator up to 10 in about a minute. So 10 to the 6 mini in about a minute. Now, to check up to 10 to the 44, this would take 10 to the 252 years. Okay, but we have more than one computer. So according to Wikipedia in 2011, there were 2 to the 9 mini computers in the world. So it's a slight improvement. That's 10 to the 243 years. But the expected time until heat death of the universe is 10 to the 100 many years. That's not a picture of heat death. That's a supernova. Heat death, there's no picture of heat death. It's just when entropy wins. But so there's some interesting kind of combination of number theory and like complex analysis that was used to find that needle in the haystack. So I want to also talk a bit about generalizations of Fermat's last theorem. So one way to generalize is to add a variable. So these are called Fermat surfaces, and we've tried nothing and we're all out of ideas. We really know very little about these. Well, okay, n equals 1 is easy. N equals 2, it's quadratic. So actually that same circle line trick works. You can write down all of the solutions when n is 2. When n is 3, there actually are infinitely many solutions. This is an example of one of the cornerstones of algebraic geometry, 27 lines on a cubic surface. It fits into some other much larger story. When n is 4, this is an example of a K3 surface. K3 surfaces are generally difficult, but they can have infinitely many non-obvious solutions. In fact, so all of these surfaces have more solutions than the curves from before. Of course, you still have the solutions where some coordinate is 0, the more trivial ones, but these surfaces have lines on them. For instance, x, if n is odd, x equals plus or minus y, z equals plus or minus w, and permutations, x equals z, y equals w. So there are infinitely many solutions, but somehow they're codimension 1. How does the geometry fit in? There's a notion of general type. This is kind of like hyperbolic for curves, higher genus. And the generalization of the Mordell conjecture, this torus thing from before, is what's called the Lang or Lang-Voide conjecture, which is that a surface of general type has not finitely many rational points, but they live in codimension 1. So here these lines are okay because they're codimension 1, lines on a surface. So for n equals 5 or greater, we know nothing. There's 0 progress. There's not a single case of n where we can prove that that fixed Fermat surface has a non-trivial solution. And we haven't found any non-trivial solutions. For n equals 4, no Melkis notice that there was a rank 1 elliptic curve. So there, for n equals 4, there are actually extra solutions to this. One big difference is that the algebraic topology of a curve has a lot going on. A two-hole torus has a non-abelian fundamental group, whereas it's much more difficult to write down a surface with a non-trivial fundamental group. In particular, all of these surfaces have trivial fundamental group. Anything that's a complete intersection has trivial fundamental group. So on the geometry side, there are just less tools to work with, no étale covers, or so on. You can also twist these surfaces. So the mathematician Swinnerton-Dyer conjectured that this surface, so it's degree 4, I've dehomogenized it. It's like Fermat, but there's a 2 and a 4. Conjectured that the only solutions were the obvious solutions, the solutions where some entry was 0. And when I started graduate school, this was a conjecture that I thought about and people thought about. I think my PhD advisor, Bjorn Poonen, might have believed this. But around 2006, a pair of computer scientists in Germany actually found some other solutions. These solutions have 7 digits in the numerator and denominator. I won't walk you through the whole brute force computation, but it would take 10 to the 16 years, at least in 2011, to find these just by trying every x, y, and z. And that's longer than the age of the universe, or expected age of the universe, which is roughly 10 to the 10. Age up to now, not age going forward. And I think the prevailing wisdom now is people think that this fixed equation, now they think it has infinitely many solutions. On the other hand, it's not a, we don't have the same tools we did for the congruent number problem. It's not an elliptic curve. We don't have modularity or uniformization. It's unlikely, I think, that we would find the next solution. It probably has, around 50 digits or so. So I find these types of things very mysterious. Even the process of predicting what you think the answer should be changes over time. I forgot to ask one question at the beginning, which was, is this a 50-minute or a 60-minute talk? Doesn't matter. I just need to know when to end.
Usually it's 55 minutes.
Okay, perfect. Split the difference. Here are some other generalizations. So Fermat-like equations. This is what's called a generalized Fermat equation. I mean, the Fermat surface was also a generalized Fermat equation, but this is what people mean. What they mean is that the exponents are no longer equal. This is no longer homogeneous, so you can't just divide by z and get a curve. So this is really a surface. When I started graduate school, the first conversation I had with Bjorn Poonen, at T, well, the first thing I asked him was, how did you win the Putnam 4 times? And so it was awkward, and he said, oh, I don't know. And then he said, well, actually, he worked all of the previous Putnams before he took the Putnam the first time. And at first I was unimpressed by that. It's like, oh, well, I guess I could have done that. And I thought, well, why didn't I do that? Anyway, then I thought of a better question, which was, what are you working on right now? It's just, if you're at dinner with a mathematician, ask them that, or ask them how they got their thesis problem, or my student Anastasia had a great one, which is, what's the first interesting theorem from your field that you wouldn't learn in an intro graduate course? So for Bjorn, this is what he had just finished writing up. So this fixed Fermat equation, x squared plus y cubed equals z to the 7th. I'll explain why this one's interesting. Well, one reason it's interesting is that there are solutions. So they're the 16 triples, the easy ones to find. There's actually another easy one. This is called the Catalan solution. This one doesn't really involve the 7, right? This solution is just 3 squared minus 8 equals 1, right? If I replace 7 with any number, this is always a solution. And then it looks worse. In the 90s, people found this solution, with slower computers. Okay, well, equations are allowed to have solutions. But then they initially missed these. And these have 8 or so digits. So what's interesting about this is, at first it seems kind of senseless. There are these large solutions. But then there are only finitely many. And in this paper, they prove that this is it. So I have 2 comments. One is, for this back of the envelope calculation, there's a trick. I like to give students who are learning to use Magma or Sage, undergraduates, this theorem, but not show them the solutions and say, find all 16, just as a programming exercise. And then they come back and they say, we let it run for a week in the background and on Emery's cluster, and it didn't find any. And it's like, okay, here's a trick. Only search over y and z and then check if the difference is a square. Okay, that's much faster and reduces the search space. This theorem's pretty difficult. The paper is 51 pages and is published in Duke just for this fixed equation. And this paper was the first time I heard somebody refer to someone else's mathematics as a tour de force. I didn't know people used that unironically, but that's how other people described this result. So what's the more general picture here? You can ask, what are the solutions to the generalized Fermat equation? X to the A plus Y to the B equals Z to the C. There must be conditions on A, B, and C. 1, 1, 1 has infinitely many solutions. Here they are. So around the time of the proof of Fermat's last theorem, Darmon and Granville, both now at Montreal, actually, proved the following theorem. If you fix A, B, and C, then the fixed equation with those exponents has finitely many coprime integer solutions if and only if this quantity chi equal to 1 over A plus 1 over B plus 1 over C minus 1 is less than or equal to 0. I'll explain a little bit more about this. This is kind of an analog of the genus in the Mordell conjecture and Faltings theorem from before. But the reason there are denominators involved is that, well, you really need an orbifold or a stack. Here's what I mean. This equation is not homogeneous. So if you had a solution where 3 divided x and y and z, you might not be able to scale that 3 away. The scaling you're allowed to do is weighted. And then when you take a quotient by that action, you get something one-dimensional, but which has some kind of extra structure. So this is kind of a cartoon picture of the stack. It's like a P1, but it has fractional points. They don't phrase their proof in this language, but this chi really is, in some literal sense, an Euler characteristic of some geometric object where you have a notion of a half point or a fractional point. And this is where the denominators come from. So the natural generalization is to ask, well, what are the solutions? So there are some. You saw the solutions where the exponent was 7. If you have 5 and 4, there's a few solutions. You'll notice, though, the exponents are all pretty small. They're all at most 10. And there's always at least a 2 involved somewhere. Now, this is the complete list of known solutions. In fact, it's conjectured to be all of them. So Beal's conjecture is that this is the complete list of solutions, as long as 1 over A plus 1 over B plus 1 over C minus 1 is negative. Now, Andy Beal is a rich banker who's an amateur. I mean, I think he has a math degree, but enthusiastic about mathematics. And he initially put a $50,000 prize on the proof of this conjecture. Eventually upped it to 100,000 and then $1 million. Or there's a prize even for a counterexample, but the prize for the counterexample depends on what that chi is. Now, I think about this problem a lot. I don't think we're going to find a counterexample. There's a project called, let me switch. There's a project called ABC at Home, which is finally shut off. If you're around my age, you might remember SETI at Home. SETI at Home was a distributed computing project to try to find evidence of extraterrestrial life. When your computer was idle, you could donate your spare cycles to search for extraterrestrial life. Well, there was until 2015 a similar project, but instead of aliens, it was interesting solutions to equations. ABC refers to the ABC conjecture, and they extensively found, what does it say here? All interesting ABC triples, so solutions to the equation A plus B equals C, of at most 18 digits, where interesting means basically close to a counterexample. Maybe it's a counterexample, but then there's an extra P. The first time I gave a talk about this, I downloaded the data, and the data, there was about a gig. Well, actually, it was about 2/3 of a gig, because you don't need to keep track of C. You only need to keep track of A and B. And so I think there's pretty good evidence. On the other hand, let me make this large again. That is Chrome. On the other hand, I do occasionally have ideas for how to solve this conjecture. None of them have worked, but it's easy to have ideas. Most of them don't work out. And as a postdoc, I tried very hard to convince my best friend, Anton Goroshenko, to work on this with me. It involved stacks. And at one point, this is when the prize was $100,000, he said, you know, the expected value of just writing other papers and getting tenure is probably higher than working on this, but now it's $1 million. So who knows how that calculation goes. Anton now works at Google in their AI division. So let's go through some examples. The 237 equation, that quantity chi is -1/42. Okay, so good number. And that's as close to 0 from below that this quantity chi can come, right? If I increase 2, 3, or 7, you get something slightly larger. So for instance, 236, this quantity is exactly 0. 235, it's positive. So in a sense, there's some heuristic that because this quantity chi is so large, that heuristic kind of allows for a few large solutions. But once this quantity gets very negative, you expect no interesting solutions. And there are examples where we can prove this. So Darmon and Mordell, basically right after they understood Wiles' proof of Fermat's last theorem, were able to take the same methods, really the methods earlier due to Ribbit, and solved all of the other families of Fermat equations that could be solved. So the next example was exponents n, and 2. Of course, you need some conditions on n. If n is 1, there are infinitely many solutions, right? And the condition from before is, well, if you write this out, you get 2/n minus a half. So you need n at least 4. And what they proved is the analog of Fermat. The only solutions to this inhomogeneous family of Fermat equations are the trivial ones, the ones that are easy to spot, where x, y, or z is 0. In fact, I'll show you a slide in a second of basically as far as you can get with this idea. So Darmon wrote a nice paper where he, in terms of the geometry of stacks, that cartoon with fractional points before, laid out basically a blueprint for all of the problems you can solve, or Fermat equations you can potentially solve with Wiles' method, and what kind of facts about Galois, what other extra theorems you would need to prove to do so. These ideas of Wiles aren't just useful for Fermat equations. Other Diophantine problems come up. So for instance, it is another ancient conjecture that the only Fibonacci numbers that are perfect powers are the 0s, 1s, 8, and that 144, 12 squared, is the final one. This was not proved until 2006. So this is an Annals paper. They needed other ideas beyond just Wiles' idea, but Wiles' idea was ideas were the thing that made them realize this was solvable. But of course, these days, people understand these techniques very well. I had a pair of very good REU students. I mean, one's a postdoc at Duke now, one is faculty at Washington. So Jesse Silliman and Isabel Voigt, respectively, who for their REU project, I said, instead of Fibonacci numbers, let's take these techniques and look at Lucas sequences. So recurrence relations that are not A plus B equals C, or fix the initial conditions, do 2, 1, 3, 4, etc. And they were able to generalize this a little bit. So a few more examples. This generalized Fermat equation, this goes back to Klein, is not an example of this theorem of Darmon and Granville. This Euler characteristic is positive. And in fact, this equation has infinitely many integer coprime solutions. The picture is not as nice as Pythagorean triples. There's still some geometry, there's still a line involved. Here's a family of solutions. So if you let f be this polynomial, I'll explain where this comes from. H is the Hessian. So the Hessian's this thing from multivariable calculus, the mixed matrix of partial derivatives. And then you take its determinant. And then T is, so that's what's called a covariant. T is some other thing coming out from the representation theory of the dodecahedron. This is how Klein was involved. I won't give you the formula. Then these three polynomials in S and T, solve this equation as polynomials. Well, at least if you normalize the denominators, which I thought this was miraculous. When I learned this, I actually, with Magma, wrote out the polynomials and plugged them in Magma just to check that this actually works, and it does. And then what this group of people proved is that, well, this formula doesn't give you all of the solutions. There's actually, in a sense, depending on how you normalize, 27 or maybe it's 54 twists of this equation. So similar degree 12 equations, such that every solution to this is given by plugging integers in for S and T to one of these. And again, the reason Klein is involved is this really comes out of the invariant theory of certain things you can attach to a dodecahedron. There's a natural way to take this equation and produce a dodecahedron. And the reason there are so many authors involved is everybody kept getting it a little wrong until Johnny Edwards, they like missed a case here or there. So even in the case where there are infinitely many, there are some extreme interesting examples. So here's the promise table. This is the progress we have on solving generalized Fermat equations. There are lots of tuples of integers where you can solve that family. So 2n, 3n. Sometimes you can only solve it for n in some range. And my first paper as a graduate student was just a single case, 2, 3, 10. This one's not a tour de force. It's only 12 pages. It's still published in IMRN. It's still in a good journal. It's not in Duke though. Building on the ideas of others. So let's talk more about the bigger picture. We discussed Faltings' theorem, i.e. Mordell's conjecture before. And the theorem due to Faltings and then later proved in different ways by Voida and Bombieri, just to recall, is if X is a smooth curve over the rational numbers, or more generally a number field, with genus at least 2, so the number of holes in this torus is at least 2, then X of Q is finite. Now, once you know that some number is finite, a natural question is, what is that number? Now, if X is a curve, there are two natural next questions. One is, given the curve X, compute exactly what that set is. So in these problems of solving equations before, you don't just want to know it's finite. You want to know what the solutions are, and you want a proof that you have all of those solutions. A companion problem is, well, if you can't do that, try to compute bounds, an upper bound on how large the set of rational points can be. So it turns out there's a ridiculous but probably true conjecture called the uniformity conjecture. It's the following. There exists a constant that depends on G, so the number of holes, such that every smooth curve of genus G over the rational numbers has at most n of G rational points, meaning this quantity, number of rational points. Of course, you can make this larger just by increasing the degrees of your equations, but if you fix the degree of your equation or fix your invariance, then conjecturally, there's an absolute upper bound that you can get. Now, my understanding, this conjecture does come from before I started my PhD. My understanding is people didn't believe this conjecture. The reason people took it seriously was in the 90s, there was a theorem of Caparaso-Harris-Mazur, which said that Lang's conjecture, so the higher dimensional version of Mordell conjecture, implies the uniformity conjecture. And people believe Lang's conjecture. Actually, they initially took this implication not as evidence for uniformity, but evidence against Lang's conjecture. And the apocryphal story, but no Melq says this is true, is that for about a month at Harvard, everybody spent all of their time trying to disprove Lang's conjecture by writing down more and more complicated examples of curves that have a lot of points. So here's a table of the best record. So there's a genus 2 curve with 642 points. That one's kind of an outlier. These, for genus 3, there's a curve with 112. And in general, you can put lower bounds. As the degrees grow, you can put some lower bounds. And there are some tricks for finding these. I do want to show you, though. Here's here's that curve. This is from Mikhail Stoll's webpage. The coefficients of this curve are kind of large. They didn't find this by trying every curve. And here are the, well, it has at least, we actually don't know if it has exactly 642 rational points. I've tried to prove this and can't. And again, some of these solutions, like this is a solution to this equation. It has, 1, 2, 3, 4, it has 10 digits. There's some interesting geometry that they use to find this, but it's also very explicit. Okay, so back to this. So I think a lot about the uniformity conjecture and have made some progress. So Eric Katz, Joe Rabinoff, and I, using ideas coming from tropical geometry and padic integration and so on, have a partial result on this. I mean, I say partial, but this was published in Duke a few years ago. And the theorem is, if X is a curve of genus G, and then there's always a catch. So the catch is, to a curve, there's some finite abelian group you can attach to it. Finitely generated abelian group you can attach to it. And we'll let R be the rank, the number of copies of Z in that group. And the catch is, we have to assume that rank is small. So at most G minus 2. You should think of this Jacobian as some kind of lattice that fits around your curve and helps you understand the curve. This rank is, well, conjecturally, this rank is either 0 or 1 100% of the time, meaning it can be larger, but in the limit, it's almost always 0 or 1. But it can be large. There are examples where the rank is larger than G. In any case, so with this assumption that holds 100% of the time, we prove that the number of rational points on X, so the number of rational solutions to the equations defining it, is at most this expression, which is quadratic in G. And in the last 7 minutes, I want to tell you a little bit about the proof and where the ideas come from. So these tools, we use, as I said before, some padic techniques, and then some ideas coming from tropical geometry and combinatorics. I'll just say for Dave, the question you asked me before, when I say combinatorial restraints coming from the tropical canonical bundle, in terms of chip firing, that's kind of like saying how many times you have to fire before you get out of debt. So you need some other tool to give you a bound on that. So here's one slide about padic integration. So Chaboutier in the 40s, and then Coleman later kind of improved and made this explicit in the 80s, showed that there are certain analytic functions that vanish when you plug in rational points. And these analytic functions are computable in the sense that I can open up magma and give you up to some precision power series expansions. So it's not appropriate to discuss much about padic integration in a colloquium. What I'll just say is there is, at least initially, a naive way to make sense of integrating on a curve over the padics. The reason this is computable is if you were to do what a calculus 2 student would do, that would work. So meaning you can solve for y in terms of x by taking a square root, but there are 2 branches of the square root. On the other hand, as long as x is small, and p-adically that means divisible by p, there's a power series expansion for this that converges. You compute it by taking derivatives. And kind of the magic of Chaboutier and Coleman is that this calculation that, you need some hypotheses, you need to prove that there's some meaningful equality here. This actually works p-adically. And then Chaboutier's theorem was, given this hypothesis on the rank, you can actually find some integrals which vanish when you integrate between rational points. Okay, that was power series. Let me show you a picture. So the idea is we have x, we have a curve over the rational numbers. We have some concrete equation we want to solve. First, make the problem worse. So first, consider the associated p-adic manifold that it embeds into. If you know a little bit about the p-adics, well, they're kind of fractal-like. And so these trees that you see coming off, these are self-similar. In fact, the the three adics, Z3, is homeomorphic to the Sierpinski triangle. I mean, it's a little fancy to say we're doing harmonic analysis on fractals. I mean, really, in a way, a lot of it's just combinatorics. But that's what these spaces really are. On the other hand, you can see there's a little bit of a skeleton to this space. So this blue, green, red graph. And then everything else, at least if this picture is correct in a meaningful way, contracts onto it. So the idea of this theorem and the theorems that inspired this due to Coleman, Stoll, and others is when you embed X into this p-adic analytic object, the rational solutions kind of live up at infinity at the boundary of this picture. And then you can still pick them out because if you take these integrals, or as we later figured out, they're really path integrals. These integrals between points vanish, I flip back, exactly when at least when the points are rational. So the way to get a theorem like this is to look at this analytic picture and analyze what these integrals look like and find a way to bound the number of solutions to them. Now, there's a second part of this picture, which works as follows. You can reduce whatever equations you have mod a prime, and sometimes when you reduce mod a prime, your curve breaks into components. So you get these little cartoons and stick figures, but then there's a relationship between this p-adic analytic fractal thing and this cartoon on the right. In fact, the relationship is really close-knit. This color coding matters. It tells you this fuzz, these trees and stuff, these colors tell you where they reduce, and this skeleton is really the dual graph of this. So the dual graph is for each component. On the right, there are two components. You put a vertex, and then if two components intersect, you draw an edge between these vertices. So there are two components that intersect 3 times, 2 vertices, 3 edges. And you can see, or guess that maybe combinatorics comes in. So last slide, and I'm just going to show you that picture again. Here is all of tropical geometry summarized in one slide. So I just described the dual graph to you. That picture from before, there's a contraction of this analytic fractal onto this dual graph. So there's a canonical way, at least in higher genus, to embed this dual graph into that fractal thing. There's a canonical contraction. And then the analysis is, so we have some, well, more generally, some function we want to understand that's meromorphic in some p-adic sense. We want to know its zeros and poles. In our application, the function is these integrals, and the zeros tell us the rational points. The idea of tropical geometry is that there's a combinatorial version of this. So if you want to understand the zeros of f, you can contract everything to the skeleton and instead study the zeros of this more combinatorial thing. So it's a theorem that this function, log of absolute value, when you restrict to that skeleton, is piecewise linear, and it's something that you can do combinatorics with. So the slope formula, this is really the key. I mean, it's something we generalize just a tiny bit, tells you that if you solve, if you look for the zeros of f kind of at infinity on this fractal and contract that, that's the same as, in a certain sense, zeros of this tropical thing. So here's our picture again. The zeros at infinity, you have your function, it's analytic, it has power series. You contract it to this skeleton, the like non-fractal part of this picture. And then you do a little, you do some combinatorics, I won't say a little, and that tells you about the number of solutions. So it takes a number theory problem, turns it into an analytic or p-adic analytic geometry problem, and then into a combinatorics problem. It's not necessarily true that the combinatorics problem is easy to solve, but we were able to. That's all I wanted to say. I'll post some references in the chat if you want to follow up on any of this. There are some excellent survey papers, and thank you for your attention.
Thank you so much, David. I see that there's already a question in the chat. Do you prefer that we continue the recording through the answer session, or?
Oh, actually, if you don't mind, cut it. I'd just like to have a
Perfect.
clean video, clean recording of this. Okay, great.
Roberto, would you mind cutting the recording?
Or it's fine if not. I'll just go for it. So
Okay.
somebody asks, why does the counterexample for the prize depend on chi? Because it's funny.
Oh, okay. So that's like just meant to be a, okay.
Yeah, I mean, it is true that the prize, well, first of all, the counterexample wouldn't be worth $1 million, so it should be a smaller prize. But he decided to make it proportional to chi, or a function of chi in some way.
I see.
Yeah.
Okay.
One other quick thing, I just posted a bunch of links in the chat, and if these disappear, you can always ask me for these. There's a bunch of survey papers. I also gave a lecture series on this topic last March, right before the pandemic hit. So there's a series of 4 videos about this that you can watch, some notes, etc.
Any more questions for David? Yeah, I wish I had the expertise to ask these types of questions, but you know, this is so far from my field.
Yeah, no worries.
Okay, well, let's thank David again.